Relativity Part 1. Let's get this out of the way, and I don't mean to sound grumpy about it, but this is my least favorite side of relativity. Why? Because it's about disagreement. It's not what physics is supposed to be about. Physics is supposed to be about finding symmetries in nature, finding harmonies, not warts. But we'll suffer through this first part in hopes that finding these warts can lead us ultimately to deeper symmetries. First, something we can agree on, the speed of light. It's always exactly c. That doesn't sound too crazy, but it is, and it's not true for bullets. Turn that gun around and the speed of the bullets relative to the ground would be slower. But this is true for light. Exactly true. Always exactly c. Now we're not saying that light is so fast that other speeds like the speed of the car can be ignored. We are saying that, well, I already told you what we're saying. I told it to you twice. The speed of light is always exactly c. Now why is that so crazy? Well, consider this and that. Two events and two observers. Explosions. The observers see these events. They receive photons from them. Photons moving at the speed of light. The closer observer sees the explosions first. Both of them agree that the explosions are simultaneous. So far, nothing too crazy, but let's put one of the observers on a train. Now right now the train is at rest. We'll replace the explosions with lightning strikes. We'll replace the yellow circles with green photons. Still it's the same thing, right? Still simultaneous, but now the train is moving. Cue the lightning. These strikes are still simultaneous to the observer off the train, but not to the other one. From on the train, we see the photon from the right before the photon from the left. They call each other on the phone. Hey, did you see those simultaneous lightning strikes? Oh, what are you talking about? They weren't simultaneous. Well, who's right? They both are. You may want to say that the person on the ground is a better or a more fundamental observer, as a better or a more fundamental frame of reference, but the ground is moving too. It's moving at 30,000 meters per second around the sun on spaceship Earth. So, tell me the truth. Are the lightning strikes simultaneous or not? That question has no good answer. It's relative. Now, I know what you're thinking. Okay, this is cute enough, but here's what you do. The observer on the train, that guy is delusional. Here's what he needs. He needs to carefully measure the speed of that photon from the right. He'll notice that it's a bit faster than the photon from the left, then do the math and no, the photons travel at exactly the same speed. I said that 3 times. And I told you, the fact didn't sound weird, but it really is weird. It destroys simultaneity. If you use bullets instead of photons, then what you were suggesting would work, but we are using photons. Again, these two new events, are they simultaneous? Yes. If you're on the train, no. If you're on the ground. Well, no, really. Tell me the truth. Are they simultaneous or not? The answer is, say it with me, 1, 2, 3, it's relative. Groan. Yeah, it's weird. And like I said before, I don't like it. So let's move on from trains to spaceships, and from observers to Martians. Now these two observers, the space traveler and the Martian, will disagree on simultaneity. And they'll disagree on other stuff too, like what time it is. Here's how the space traveler keeps time. She fires a photon from the floor, lets it bounce off the ceiling, and then land back where it began. 1 space traveler clock tick. Nice. But here's what the Martian sees. He sees the photon travel a much larger distance. No big deal if you're using bouncy bullets, but since relativity is weird, both observers must see the light moving at exactly the same speed, which doesn't add up unless we stretch time. Now, for simplicity, we'll look at just 1/2 of the photon's path. Here's the equation for the space traveler's half-clock tick. And the Martian sees the photon go further. Pythagoras will tell you exactly how much further. But this happens in the same half-clock tick. So take that and math. Got it? Good. And we'll welcome back the space traveler and her expression for the half-clock tick. Let's put these guys together. There it is. The equation for time dilation with gamma. Gamma, the famous Lorentz contraction factor. The Martian and the space traveler are aging at different rates. That's not just weird. It was tested weird in the 1970s with a jet. Behold the Haffel-Keating experiment. Look it up. These guys synchronized 2 atomic clocks. They put one of them on an airplane, put the airplane in a trip around the world, and then afterwards, the clock that had taken the trip really was younger. It didn't seem younger or appear younger. It was younger. Literally younger. Literally less time had passed in the air than had passed on the ground. Weird. And there's more. Time dilation meet length contraction. This part is worse. Off the airplane and back into space. Now that the space traveler has a clock, she wants to measure her living space, and to do this, she'll bounce a photon back and forth and measure the time for the round trip. The Martian sees the same photon as it makes the trip. Unlike the last example, this time we'll have to do both halves of the trip because, yeah, they're different. They're different, but not for the space traveler. Things work out pretty nicely up here. It's messier for the Martian. The first part of the trip, as you can see, is longer than the second, and we have to keep in mind that these two are using different clocks. So working off those expressions, working, and remembering that time still adds up, that's a relief. Now math, and take a breath, and rearrange with the Lorentz contraction. Got it? Then, bring in our old friend the space traveler back and her different speed clock. Okay, welcome back. We can now rearrange, and now we have 2 expressions for Tm. So let's get them together. And we are but one step away from this, the equation for length contraction. And what does it mean? That's a good question. It means that lengths, like times, appear different to different observers. They are stretched or squished by gamma, the Lorentz contraction factor. And this means that the Martian will measure a smaller value for the length of the spaceship. The space traveler to the Martian, the space traveler, as she moves, will look squished. And she'll be aging more slowly. She'll be younger, really younger than the Martian. Or look at it this way. Classical physics was like a stage. Everyone agreed on a few basic things, like how to measure time and distance. We could all agree what time it was. If your directions were to wait 5 seconds and then walk 5 meters stage right, we could all agree on what that meant. Not so with relativity. Instead of that one big clock thing, everybody now wears their own wristwatch and carries around their own meter stick, which raises the important question, the question I've been waiting for. Isn't there anything we can agree on? Well, find out in part 2.